after the end of today, you will have some idea of how this works. And if you don't, you ask, because this idea underpins a lot of what's about to happen in Chapter 3. Chapter 3 is very different because we start doing chemistry. Yes, it's acid-base chemistry. You know something about acid-base chemistry, but you know about 5% of what you need to know for acid-base chemistry in this class. The rest of it will fall into place if you take this seriously. We left off on Friday with this picture of acetate anion, and this idea that this molecule has a known structure, and we can draw more detail. We can put some lone pairs on, which I encourage you to do, so you know where the chemistry will happen, and you know where the sticky parts are. And we said that that looks an awful lot like a molecule in which the carbon-oxygen bonds are different. One looks like a double bond, one looks like a single bond. And double bonds are shorter than single bonds, so if you measure this structure here, surely they should be different. Well, no, when people actually did get down to measuring these structures, it turns out the bonds are the same length. So how on earth can you reconcile this double bond and this single bond being the same length? And this is where the idea of bonding started to develop, and this idea that in many cases, electrons are not localized. I need to use two words today that you need to pick up very quickly: localized as opposed to delocalized. Localized means they are sat on one atom, and that atom has them completely. Delocalized means they're spread around. They are shared amongst different atoms. And I'll repeat this as I go through. Localization tends to maybe destabilize something in a charge, and delocalization tends to stabilize things. If you can spread things out, you can share the pain across different atoms, that will stabilize a molecule in general. I need to do several different types today. I need to talk about positive charges and negative charges, and later on in the term we'll do radicals, which is somewhere in between, but the concept is the same for each of them. If you understand the idea of delocalization, you can start to get into Chapter 3. And Chapter 3 to me is the beginning of the real chemistry. The actual structure of that molecule looks more like that. And chemists had to develop these devices to be able to show partial bonds. Yes, this is a partial bond. And in this system in which we're sharing between two equal oxygens, you could argue that one of those bonds is 1.5 and the other bond is 1.5. In other words, the pair of electrons are now spread out over two different atoms, and that gives you this sort of blurred looking picture in which what we call delocalization. This is tricky. This is not easy to get hold of at all. We start out by trying to get our heads around this stuff by looking at what we call resonant structures. And these are Lewis dot structures that you can draw for that species. Sometimes they're equivalent, sometimes they're not, but they help you get a handle on where the charge can be. So what we're saying in this system is that one of the lone pairs on this oxygen seems to be spreading out and being pushed towards the other oxygen. This is probably the first time we've seen the curved arrows. It might well be the first time we've seen the resonance arrow. So different types of arrow that we use to show different types of information. The curved arrows are to show electrons moving around. But that's a problem with resonance because electrons aren't really moving around. But we sometimes use the arrows. The book will use the arrows. I'm not a big fan of it, but it might help you get into what we're doing here. We are spreading, I used the toast analogy on Friday, you're spreading that butter across that piece of bread and it's spread out, it's delocalized. It's not at the left, it's not at the right, it's spread out across the whole system. And we can show that using arrows, and what that will allow you to do is to get to the other resonance structure. Because the other resonance structure now looks like I put an extra pair of electrons between those two atoms, therefore I ought to draw a double bond right there. And this second arrow looks like I'm taking a pair of electrons from the pi bond and putting them onto the oxygen. So that pi bond looks like it's becoming a lone pair and localizing itself onto the oxygen. So that will allow me to draw the resonance structures. And on many of the questions that are about to happen throughout the whole 2 semesters and further, we'll have to be happy with resonance and what it is and what it does and how it's allowed and the consequences. So I'm going to take my time on this. Maybe I'll get finished with this today, or maybe I'll spend a fair amount of time on it. Certainly in recitation, certainly in office hours. We'll do many examples, and hopefully you'll get comfortable with it. So what is it? It's electron spreading out. There's some requirements for this. You need to have pi bonds. You need to have atoms adjacent that will have pi bonds so that we can move those pi electrons around. I looked at these on Friday. I said that these are typical examples. Don't worry if you don't get this just now. Hopefully by today, tomorrow, recitation, whatever, you'll start to get a handle on this stuff. It is essential that we do. So at the top, I've got a system in which one of my lone pairs, doesn't matter which one because they're all the same, seems to be delocalizing onto the other oxygen. If I do that, my electron count on this oxygen becomes 3 lone pairs, and negative, and the electron count over here becomes 2 lone pairs, and it becomes neutral. Again, be careful. This is not equilibrium. I'm going to write this down, and hopefully it starts to sink in. It is not shifting between those two structures. That's absolutely not what's happening here, because these pictures are not different. These are part of the same molecule. They're an attempt to draw where the charge can be in a single molecule. The best we can do with Lewis dot structures. We'll see some of this stuff as we go through, certainly next term, a lot of it, and most of next term is based on that idea of carbonyls and C double bond N being delocalized in such a way. Ashley? hybrid. Yes, yes. Now, the thing to do today is to go back a little bit and to start some, underpinning. Where is this? What's it coming from? Where's it coming from? Why is it important? Where does it come from? What are the physical requirements that you have to have in a molecule for this to happen? So we'll go back to one of the easier ones. We'll start off with a positive charge, and I want to point some things out. You may have read them in the book, but I haven't said them in class yet. Good grief. Are you okay? You stay back over there. What is a positive charge? What do we recognize a positive charge as being? Well, in this example with a carbon, we've stripped back a lot of information. And that, what we call a carbocation, you all know what a cation is. This is a carbocation. It's missing a pair of electrons on that carbon. So it only has 3 bonds. And that positive charge there is an empty p orbital. You'll see this in the 5th, 6th chapter when we get there fairly quickly, around the first exam. That is an empty p orbital. If you had to look at the hybridization of this thing, it has 3 single bonds. What shape will that adopt if it has 3 single bonds? Trigonal planar, right? And what's left over is a p orbital. And that p orbital becomes very important later on. But right now, we've got this issue about the fact that this thing over here lost a pair of electrons. The carbon at the end only has 6. And it would be nice if it could get some help. It's lost a pair of electrons. Maybe there's something in this molecule that can help it out and stabilize it. Well, not necessarily here just yet. We don't have a pi bond. If we have a pi bond on the left, all we've swapped out here is we've taken out a couple of hydrogens from this molecule and we made a pi bond. That pi bond is a couple of electrons, the pi electrons, that are loosely held. I think we got this out of the way in the first chapter. Single bond electrons are tightly held because they're right between the nuclei, and the pi electrons are above and below. They're further away. So they're not as tightly held, and they're easier to give away, easier to share, easier to delocalize. So what we'll start doing today is saying that carbocation could do with some help. And if I have a pair of electrons over here that's not really doing anything, I can borrow them. I can share them. I can spread them out across this system to help stabilize this compound, this carbocation. Well, we need to put some information back in. This picture kind of helps with this. You need to have that pi system because you need to have adjacent p orbitals. You think what I just said about this carbocation being an empty p orbital? Well, if I have the pi bond next door, they're also p orbitals. And if you form a pi bond, what's needed there are 2 p orbitals parallel to each other so they can overlap. And the overlap is a bond, and it helps. In this example, the carbocation on the top left, this is this. I have an empty p orbital on the right, and I have a pi bond next door. So I can borrow some electron density from that pi bond to help out this carbocation at the end. Why? Because it only has 6 electrons. So we'll find out now that delocalization in this type of positive charge is only necessary when you have pi bonds next door. They have to be right next door, else it won't work. And it turns out this carbocation is much more stable than this carbocation. And I've got the terms again. If I look at this slide going backwards, on the left it's delocalized, it's spread out. On the right it's localized. It is stuck on one atom. So a general term you can say, a general sort of statement you can make today, if you can delocalize a charge, you stabilize that species. Write that down. Delocalization helps stabilize systems. You'll see where it comes in chapter 3 very, very quickly when we start predicting chemical outcomes. So this little picture here of these 3 atoms, you'll find all the way through the 2 terms. When we got the benzene chemistry, 2 chapters of it next semester, you'll find that understanding that little allyl cation really is the key. Recognizing that this can show up in all sorts of different places. It looks like it's buried in different places, but it reveals itself, and then you can put this into practice, and this is a good system. So the one on the left is more stable than the one on the right because it can delocalize. The one on the right is localized. That's not as good. I've got some molecular orbital theory. There is a lot more of this to come next term. Some of this, not a lot more next term. This idea of thinking about what the constituent pieces are that go into molecular orbitals, and they are, of course, atomic orbitals, and then thinking about how they come together to make bonds. So in this case, why do I have 3 levels? Well, fairly simple. I have 3 atoms with their orbitals, and we're talking about the possibilities for overlap of those adjacent orbitals. Now, what's the best situation? They all overlap, they all ignore each other, some overlap, some don't. What's the best situation? They all overlap, because overlap is bonding. The more overlap you get, the more bonding you get, and bonding is good. What's the worst situation? Anti-bonding, right? Where they're ignoring each other, they're repelling, they're destabilizing each other. So this picture is trying to take our resonance structures over here and explain how this actually happens in reality. At the bottom, I have a bonding molecular orbital in which all 3 of those pi bonds came together, or those p orbitals came together. And that gives me a nice picture in which everything's overlapping, and we're good. Now, the non-bonding we haven't talked a lot about, so we'll see that more next term, but this is where they just ignore each other. There's no interaction between adjacent orbitals. That's a higher energy because they're not overlapping. And at the top I have the worst, where everything is ignoring each other and actually destabilizing each other, and that's the anti-bonding orbital. So from the past, I could draw these horizontal lines to represent these orbitals, and I could fill this in quite quickly. This isn't too bad. How many electrons am I dealing with? How many electrons in this system, how many pi electrons in that system do I need to put into my picture here? What's the positive charge? How many electrons in that positive charge? How many electrons in that p orbital? None. A positive charge is an empty p orbital. How many pi electrons in that pi bond? Not a trick question here. In the pi bond itself, how many electrons? How many? 2. Yes, 2. So I don't have any electrons in the p orbital here, and I have 2 pi electrons there. So how many electrons total to put into my picture? Not a trick question. 2. Yes? So where are they going to go? Down here in the sigma, up here in the non-bonding, or up here in the sigma star? At the bottom. Okay, we hopefully have learned some of these things. No trick questions here, just adding the stuff together, making it logical, hopefully just extrapolating a little bit. So is that good or bad? Both of my electrons are in a bonding situation. Is that good or bad? Good, it's great. That's why this is a good system. You can't do that with the other system. You can't do that unless you have the pi bond. So now I can start thinking about how I can represent this. What looks like happening between these two pictures is that this bond, or these electrons, are being pushed over there. So that they were being shared between the two carbons left and right, and now they're being shared between the two carbons from the middle to the right. But again, be careful, it's not dynamic. We're not doing this. I keep writing this down and crossing it out because it's not equilibrium. We're not shifting between 1 and 2. That's really important to get your heads around. So again, these two pictures are the best we can do for drawing sort of representations in a Lewis dot structure. What does it look like overall? It looks like a hybrid. It looks like a situation in which I've got some partial bonding between those two atoms, between all those atoms. Now I have several ways of drawing this resonance hybrid, which we'll show you in recitation and office hours as much as you want. I could draw a positive charge in the middle, which is suggesting that the charge is spread out over the whole system. What else do I have? What other device do I have to show little bits of charge all over the place? Delta negative, delta positive. So in this system, if I draw this thing out again, and I draw a hybrid in which we're trying to show delta positive, what about, does delta positive go in the middle? No, right? None of those carbons ever become positive in the middle. So I'm going to put delta positive over here and delta positive over there, and that's a pretty nice, useful representation of that molecule. And you'll see next semester that you can attack both those carbons because they both need electrons. So the localization is important. It helps stabilize things. We've got to build up very quickly a picture of why this happens, how this happens, and what the requirements are. Anybody want to say anything? Okay, those of you who are still in chapter 1, good luck. Some things you don't do. Tyler and I have discussed this, and we've agreed that sometimes it's best to show you what not to do so that you can learn what to do, or at least to understand why you got things wrong. Well, we're using these arrows. These arrows will be the rest, they will take hours and hours and days of your time from now on. This is where people either get organic chemistry or they don't. We are using arrows here to represent electrons being pushed around. Now, one of the problems here is that I am breaking bonds. That's not happening in resonance delocalization. I am not physically snapping anything apart. This is a problem because this is a chemical reaction. That is not represented by a resonance arrow. A chemical reaction requires a chemical arrow, which would be something like that, or it might require an equilibrium arrow. This is not happening here. If I'm trying to show delocalization, this is not a valid representation of that. Okay, you're breaking the connectivity. I've used that phrase again and again, connectivity, how the atoms are joined together. Nothing's changing here. The connectivity, write this down, the connectivity in resonance structures is retained in all the resonance structures. Connectivity is the same in each of the resonance structures. I'm not breaking any atoms apart here or breaking them off from structures. So that's one basic thing to look out for. Don't be snapping bonds. Next thing, don't break the octet rule. Okay, you cannot break the octet rule even in Youngstown. This thing is a rule. It is a fundamental principle here of chemistry. We're not going to be breaking anything. We're not going to be giving any of our elements 10 electrons. So if I think about this, why is this not a good arrow? Well, my oxygen seems to want to spread, and that's okay because it's localized as it is, but I don't have any pi electrons. That's really the key here. There's no pi bond right there to help out. If I have sp3 carbon right there, this won't work. Because if I push electrons into sp3 carbon, it already had 8, it would then have 10. That just doesn't work, so don't do that. Likewise on the nitrogen in the middle, this wants to spread out if it can, but there's nothing here. In a positive sense, there's no pi bond. We don't have the requirements for delocalization, so we can't do that. On the right-hand side, likewise. These would all be 10 electron systems, and that just doesn't work. And in fact, you think about this. You think about those orbital diagrams you've filled up in the past. If you try to push 2 more electrons into those other atoms, all the bonding orbitals are full already. So where would the 2 electrons have to go if they could go there? If I were to push these electrons in towards that carbon, do I have any available orbitals? All my bonding orbitals are full. Do I have anything available to push into? What do you get when you mix things together? You get bonding orbitals and you get anti-bonding orbitals. So you do have the space, you do have the volume maybe, but is that a good thing or a bad thing? Bad, terrible. Yeah? So there is a logical reason behind why you don't draw those pictures. Because you'll be populating anti-bonding orbitals, and this idea is stabilizing, not destabilizing. So don't be doing anything like that. And again, in recitation, I'll do this, and Tyler will do this in SI. We'll give you some examples of what not to do, so you can hopefully pick up what to do. So resonance, you need to know it. If you don't, this is no fun at all. The book gives you some ideas of how to get into this. It's one of those topics that if it clicks immediately, it's a piece of cake. If it doesn't click, it's a nightmare. Right? It just doesn't make any sense. So we can sit down in office hours, we can go to the chalkboard, wherever you want to make this work. The more examples you see, the easier it is. So you're given a picture like this, and this is often a question on a first exam or a quiz. Here is an organic molecule that is real. We can measure it, we can see it, we understand it, and we know it's stabilized by delocalization, by resonance. So how do you get to show that? How do you draw the other resonance structures? Well, we'll find that one of the major goals here is to push electrons, negative charges, away from the atom that seems to be holding them, to spread them out. I have the requirements here. I have a charge next to a pi bond. That's my basic requirement for this, in both the negative, the radical, and the positive sense. You must have a charge next to a pi bond. So looking at this idea now, I can use my arrows. My curved arrows are suggesting that the oxygen is sharing with its neighbor. That would give the neighbor too many electrons, so we have to push 2 more across. Now, you only have to count to 3 here. You're not going to push to the 4th carbon or the 5th carbon. Okay? For the next resonance structure. It's going to be 3 atoms away every time. Well, what that gives me is this second picture. I'm not going to say second structure because these are the same picture. These are the same molecule. I'm just trying to show where the charge can go. On the right-hand side, I seem to have put my extra lone pair onto the carbon next to the carbonyl. That's a good thing. But I seem to have lost my negative charge. What do I need to put in here to make it balance? I can't lose charge here. I can't destroy charge. I can't create charge. So where do I need to go? What do I need to do here in this picture to make it make sense? I need to put a negative charge someplace. Wake up! Don't fall asleep in my class. You know who you are. You won't do it again. You need to put a negative charge there because you need to balance it. It needs to be the same charge on the left and the right. And that's shown at the bottom. And there you have 2 valid resonance structures for that species. This is the way to do it. This is where I think the arrows are useful. These curved arrows, they're a bit dangerous later because you think this is a chemical reaction. It isn't. You think this is a mechanism. It isn't. You're using the same device to show 2 different things. This is allowing you to get into working out where the charge should go so you can work out what the actual thing looks like. Now, if you were to draw a hybrid for this, and I'm not sure this is on the slide, so let's have a go at that. The connectivity stays the same. So the first thing you do is you write down all the atoms in the same places. And then you start to show where the delocalization happens. Well, I think I've got partial bonding here, and I think I've got partial bonding there. That's it, 3 atoms, no more, just yet. Now, that doesn't quite take care of the whole picture. What's missing from my picture from there? The negative charge. And I'm going to be careful here. The negative charge is spread between the 2, and I certainly can write delta negative on the O, and I certainly can write delta negative on the carbon. Then we get into this idea later of what does the molecule look more like? The simple examples we started with, it looked like the second resonance structure was pretty much the same as the first one. They didn't look that different. Now I have pictures in which I've got some charge on oxygen, and I've got some charge on carbon. Where do you think there's more charge? On the oxygen or on the carbon? On the oxygen, why? More electronegative, right? What we're doing very quickly now is putting the ideas together. That electronegativity idea is now building into resonance, which builds into acid-base chemistry, very quickly coming up. So we've got to be careful now, and we've got to be comfortable with the overall idea. So we'd argue later on that this resonance structure seems to be more significant, or in English, the molecule looks more like that resonance structure. not the other one. There will be more charge on the oxygen because it is more electronegative. But spreading the charge out is beneficial. That's why this happens. Are we okay so far? This picture does not look anything like the previous one. The previous one had some oxygen, it had this double bond, we stripped away a lot of hydrogens, we made this thing as simple as we possibly can. That system at the top looks nothing like the one I'm about to show you. But they are the same, essentially. They are the same thing. They have 3 atoms set up in a system which has a negative charge, which can spread out through resonance delocalization. We have the same requirements. We have a lone pair. Doesn't matter what atom it's on, it has a lone pair. It's got an extra lone pair that constitutes a negative charge, and we're going to push this around because it will help stabilize the system. And I also have my pi bond. That's what you need to have next door. No pi bond, no delocalization. So, thinking about using arrows to describe this, you might be given this picture, and your job is to come up with that picture. You can think about taking this pair of electrons and pushing them towards over here, so that this pair of electrons goes on to the other carbon. Same 2 arrows, 2 in, 2 out. I can't just use one arrow because that would give the central carbon too many electrons. That's illegal. So I've got to compensate. I push 2 in, I've got to lose 2 to give me my other picture. Again, it's not equilibrium. It is delocalization, trying to do our best job of trying to show where the charge can be. So I'm going to draw this allylic carbanion this time. Spend a lot of time on this next term. And I could show that as a resonance hybrid to show what it looks more like. Now I'm dealing with 2 oxygens. They both seem to have 2 hydrogens. I'm dealing with 2 carbons, both of which seem to have 2 hydrogens each. Where do my delta negatives go? On the end, not in the middle, never in the middle. Delta negative, delta negative. Now, look at that system compared to the question we just asked on the previous slide. Oxygen seemed to hog some of the electron density on the last slide because it's more electronegative. What do you think here? Equal distribution or different distribution of delta negative? Equal because they're the same atom with the same electronegativities. All of this stuff is logical if you've been keeping up. That's the key, is keeping up. So there's my resonance hybrid for that guy. Again, recitation, we'll go deeper. We'll give you dozens of examples in which you can see this applied in bigger molecules, more scary molecules. It's the same deal. It is 3 atoms. It's only atom 1 and atom 3 that get charged. Bottom, again, this is similar to the one we did on the previous slide, but it's also exactly the same system to a chemist as the one above it on this slide. This one doesn't seem to have any heteroatoms. There's no nitrogen, no oxygen. This one down here, yes, it does. So we can start to apply the idea, and we can start to think about where charges will go. If I wasn't given the picture on the right, I would take my charge and I would push it here. Why am I pushing this pair of electrons? Because that's my imbalance, that's my negative charge, that's my instability. Why not push the lone pair on the N? Well, how many lone pairs does N have when it's neutral? 1. It's quite happy having a lone pair, so there's nothing unstable about that lone pair. It's the negative carbon that's unstable. That will become very apparent soon when we do acids and bases, and we start thinking about where the charge can go. So this is my second resonance structure. I got that by pushing some arrows around, and then I can draw a hybrid. And my hybrid, again, the connectivity is the same. And I just draw some dashed lines to show the delocalization around there. I can put delta negative on the N, and I can put delta negative on the C. Where do you think more of the charge is, N or C? N, why? More electronegative. What is its electronegative? 3. Yeah, 3-ish. Carbon is what? 2.5. Basic, simple, fundamental rules of the game that we're now starting to apply. If you don't know your electronegativities, good luck. We can do this with whatever you want, and we will in recitation. We can start to draw this thing in all sorts of different systems to hopefully hammer home that it's the same idea. You get it once in a simple system, it's the same regardless. So I'm looking again at the one we did previously, where I had the one that we had previously had a negative charge up there, but this is a little bit different because it's neutral. That is still a lone pair. I still have lone pairs. Now, this isn't so apparent just yet. It's a neutral molecule. Why should it do this? Why should we delocalize? Well, the answer again is to help spread things out, to help spread electrons out. That's always a good thing. But when we get to the chemistry of some of these things next term, and we think about the possibilities for reactions, we'll find that the carbon down here is quite reactive. Okay? The carbon at the bottom right is actually quite reactive. That is not represented in this molecule by that picture. The reactivity, the fact that it's delta negative, it's basic and it's also reactive with positive things, is set up set up by the fact that we can spread some of that lone pair onto that carbon. So this will explain reactivity next term, this idea of delocalization, the idea that it's a good thing, and now all of a sudden we can see where the reactivity of that thing comes from. where it doesn't seem so reactive in the picture on the left. In the middle, likewise, we'll find that in spectroscopy. Spectroscopy is a huge chapter, 2 chapters that we do next term. The physical properties of this carbon that I'm pointing at are a little bit different to the physical properties of a ketone. Well, they both look like a carbonyl. They both look like they have delta positive C right there. Why should the physical properties be any different? The answer is, this ester has a lone pair. That lone pair can delocalize, it can spread out. It changes the chemistry, it changes the reactivity, it changes the physical properties of this carbon, because this guy can do it and this guy can't. Very subtle. But now, 20 weeks away, long time away, this is going to be important. And you will remember, I think, looking back, you learned all the important stuff in the first 4 weeks. If you learn it and you can use it, the rest of the 2 semesters is great. If you didn't, it's just a disaster. Down at the bottom, many of you want to do biochemistry in the future. You should. This idea of delocalization is very important in amides. The amide functional group underpins proteins. And you'll see now that these things are much more complicated than they look, because it looks like I'm putting some double bond character right there. So that means slow rotation. Single bonds rotate quickly. Pi bonds don't rotate. If this is somewhere in between, maybe it rotates slowly. We'll get there next term, but it's all based on this fundamental understanding of this idea of resonance. Anybody? Hello at the back. Yeah. 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 I don't do that. Yeah. Tommy, right? Yeah. No. You'll find out when you practice the old exams and you practice my problem sets. Okay? You'll find out where this comes in. And very rarely, maybe for one 5-point question on the first exam, you might be asked to draw some resonance structures just because. The rest of it comes, it's then apply the resonance structures in this much bigger problem, knowing that you understand what delocalization is about. Yeah? So we will get there soon. Lilic carbocation. We drew this before. We want to try and get out some idea of where we see these things. Pattern recognition. These things tend to be embedded in bigger systems. A lot of the next term is bigger systems heading towards biology, heading towards engineering. And the molecules have to get bigger necessarily. So there's the allylic system. Nothing too scary. It's only 3 atoms. And I have a need for electrons here. I have a pair of electrons here that can help. I can spread them out. I can draw a second resonance structure in which it shows delocalization. I can draw a hybrid. And that helps me understand why this is a decent system. Well, you start to embed these things in bigger molecules, which you have to. You can see where this comes from. Not all the resonance structures appear at the same time. They don't all reveal themselves at the same time. So on the left, I have the allylic system with a bit of extra stuff added. If I do this idea now of delocalization on the left, I can draw this resonance structure. But guess what? Embedded now there, that just revealed itself, is a second allylic system. You have the same requirements now in this picture. So it should make sense that that can delocalize as well. By the time we get to 3720 and we talk about benzene, you'll have to draw 6, 7, 8, 9, 10 resonance structures to explain the relative reactivity of this versus this. That's deep. That takes a lot of effort, a lot of discipline. So we are dealing with the basics, the very simple ideas here of what it constitutes a resonance system, what you need, how you draw the arrows, how you draw the structures, and then in 3 we'll start to use them. This one you'll see next term, not so much now, but this one to me is the most logical. That is a negative charge with extra electrons. That looks like a positive charge that's missing electrons. Why not just get together and make a bond? Well, that's what happens. But the chemistry of this stuff is all explained by the fact that this guy is delta negative and this guy is delta positive, and we can explain that by that resonance structure. In that pi bond, where the electrons are going to be weakly held, they're going to be pulled towards the O more so than the C. The O will be electron rich, and the C will be electron poor. I've said that before. Those terms will become important now. This will be electron rich, absolutely, because it's more electronegative, and this carbon will be electron poor because it's losing out. It's not as electronegative, and it's losing out, so it will react with negative things, whereas the oxygen will react with positive things. That will explain an awful lot of the second term. So these are systems in which we have a charge next to a lone pair, and that lone pair can help out. As you practice, you start to see what is called pattern recognition, and at the bottom, this system doesn't look like anything like the one above it, but it is very similar. You have a positive charge, which from today is an empty p orbital next to a lone pair. That lone pair can help out. It can spread, it can delocalize, and you can draw the second resonance structure. That's good. Now, practice the problems in the book, do the online stuff, do some of that Orion stuff. Some people have, some people haven't. That builds a foundation. If you have a shaky foundation going into chapter 3, we find out very quickly. If you practice those problems and you get some of them wrong, go ask why, work out why, build that foundation. It's all about foundation from today onwards. Which of these two resonance structures do we prefer? We have this over here, which has 6 electrons on that carbon, and we have this over here, which seems to have 8 electrons here and 8 electrons here. Which is better? The one on the right. So the molecule will look more like this, because that has all the octets satisfied, and less like the molecule on the left, because we have one with 6 electrons. Simple ideas, you practice them, it sinks in, and we get to use them. And I would argue, in the bigger picture, this is the last of the basic rules, other than maybe steric environments, which we'll do later, that you have to know to be able to play this game. If you're okay with them individually, the next step is to put them all together. Use the rules together to solve problems. Big day today. I'm not going to spend any time on this because this is a great story 20 weeks from now. Yeah, this is a long way away. This does happen. We do have this idea of double bonds and then sort of delocalizing around a cycle. That's a big deal in 3720. I'm not going to ask you much about that just now. It's in there to show you that it's important later. You're going to deal with simple molecules that we've just seen that involve carbon, nitrogen, oxygen, in which the molecules are fairly small. Right, finishing this off. Some rules from the book. Try and minimize your charges. If you think about this over here, this looks like charges building up on the O, this looks like charges being lost on the N. You'd have to argue that maybe the one on the left is more important because we don't have any charge separation. Charge separation typically isn't a great thing. But on the right-hand side, this is important because you do have some pi bond character. That will become important later. And you'll notice something here. Electronegative elements are able to be positive if they have an octet. You know that already. What's the simplest example of a molecule you know that has a positive oxygen with 3 bonds and a positive charge? Hydronium, right? And hydronium is great. So that is a central oxygen that has 3 bonds. It has 1 lone pair left over. It has 8 electrons, and it can be positive. But you will never see something like this. You will never see O with 6 electrons and a positive charge. That just doesn't happen. That is horrible. That is illegal. Let's just get rid of it. Didn't even happen. You can't have a 1-bonded oxygen with a positive charge because it's so electronegative it will never allow that to happen. 3 bonds, yeah, because it's got an octet. You'll never see oxygen with 6 electrons. That shouldn't add up. So to finish that off, and to get into the next chapter, on the left is the definition of localized. No pi bonds available to push charge around. On the right, yes, you can delocalize. Yes, you could argue that lone pair here can push into this double bond over here. We can draw a second resonance structure. How important that resonance structure is based on electronegativity values, stuff like that. But localized typically isn't as good as delocalized. What we need to do is to put that into practice. And that's chapter 3 coming up in a second. Examples that I did the other day. This is recitation. If you're not in recitation, you're not happy with it, come find me. Come find Tyler, whatever, go to SI. Get this stuff organized now, or else you get lost, and you never get back. So I reckon that's the end of chapter 2. I'm into the second week of class for real, so I reckon that's good. What I'm going to do now is change your lives forever. For the better, hopefully. You all know what acids are. You all know what bases are, but you've never looked at them like this. You've never looked at big organic molecules like this and recognized acidic components, basic components, and what they're used for. You will find as you work your way through here, carboxylic acids, you notice the functional group, they are acidic. Hydroxyl groups are acidic. Carboxylic acid groups are more acidic than hydroxyl groups, even though they both are OH groups. We have to understand why. For those of you who have, do want to go to pharmacy school, med school, graduate degrees in biology or biochemistry, the amino acids are a marvelous set of molecules because they contain both acidic functions and basic functions. And there's this marvelous interplay between them at physiological pH. You have to worry about isoelectric points and where are my protons, which residues are protonated, which ones aren't, so where does my binding happen. Morphine down here. I have a functional group that you know right now is a hydroxyl, but we'll define it in a minute as a phenol. And that thing is acidic. It's actually more acidic than this guy down here, even though they're both alcohols. That's subtle. And I have over here a lone pair. I've told you to try and practice putting lone pairs in because they do the chemistry. In the acid-base chemistry coming up, it's all about the lone pairs. So this is basic, and these two are acidic. I have a polyfunctional molecule that can do both, depending upon the environment. And I think that's key to understand for these ideas coming up. It depends upon the environment what will happen. If the reaction is basic, something might happen over here. If the reaction is acidic, something might happen over here. You're putting things together that you've seen before, but in a much more detailed way. This is challenging. Strychnine, I've got lone pair here, that makes it basic. I've got nitrogen here, not so basic. We'll understand why, because it can be localized. And those are the types of compounds that you will see from now on that you have to tackle and be able to give rational answers as to why what happens. This is not trivial at all. So those of you who've been keeping up, this will get more interesting. This will get more challenging. It'll get more realistic. So we start out by going back to what I hope is high school chemistry for most of you. I'm not quite sure how it works here. I think you get some chemistry in high school, then you go to the freshman class and they make sure you get some chemistry. Everybody should be on the same page with these ideas so far. We know from the past that there are several definitions of acids and bases. We know there's an Arrhenius definition, which is way out of date in terms of acids having just a proton, and hydroxide is the only base around. It isn't, obviously. And then we move to the Bronsted-Lowry idea, in which acids are proton donors. Everybody in the class should know that. And bases are proton acceptors, conversely. That definition, or those definitions, will not be enough for this class. We'll have to talk about Lewis in more detail and talk about how that sort of brings everything together, a more sort of a global type of idea for acids and bases. But everybody here should be able to point at that and tell me it's an acid. Not because it has a proton, right? We'll see why in a second. It's not acidic necessarily just because it has a proton. A lot of the acids we deal with don't have protons. That's tricky. We have a base, which has got some lone pair acceptors. I mean, we've got proton acceptors, that essentially is a lone pair. So water can be a base. And if I do my chemical reaction somehow, and I don't think you've seen this yet, somehow this molecule communicates with this molecule, and they magically end up over there. Except it's not Harry Potter. There's actually rational ideas behind this. How does this happen? Why does it happen? I've got 10 minutes now. I'm going to start on this, but obviously Wednesday is the big deal here. If you had to tell me in this molecule of HCl where I should put delta plus, where would it go? H or Cl? If you said Cl, we've got problems. Right? That's the delta plus, delta minus setup. You've got problems, you're not getting them solved, good luck. If you want to get them solved, come ask. In this molecule, where's the delta positive, delta negative setup? Where's delta negative in that molecule? Oxygen, plus it's sticky because it's got lone pairs. So I'm thinking now that my lone pair could be used to go over and grab that H, because it's negative going for positive, and that bond breaks. And we have drawn our very first mechanism. And 99.99 times out of 100, it's mechanism that gets people here. If you get mechanism, this is great because you can use it to predict. If you don't, you don't. On the right-hand side, I have something called a conjugate base, as you see at the bottom. I have something called a conjugate acid, as you see abbreviated down there. And I have a chemical reaction. That's the first chemical reaction you've seen in my class. But it's a very common, very simple thing that you've seen many times before. And you have some idea of how this works, and you've probably done this yourself. If you dissolve HCl in water, what happens to the container? Does it get hot or cold or stay the same? It gets hot. Why does it get hot? It reacts. Okay, it reacts and it gets hot. Why does it get hot? What's happening in the reaction? Are we becoming more stable or less stable by doing this? Is it endothermic or exothermic? It's exothermic. That's why it gets hot. Yeah? So those ideas, the fact that this is a very strong acid, this is a weak base, and this is a very good conjugate base, and that's a decent conjugate acid, now have to come into practice in the organic world. So when I use these terms, you should be happy with them on that very simple system, because my systems are about to get very complicated, at least compared to what you've seen before. So there we can think about water. Water is something we need to head towards because it's the solvent in biology. My job is to get you into things like biochemistry and polymer chemistry later on. And we can argue now that water is very, very versatile. It can serve several purposes. It's one of the simplest molecules you ever see, but it's also one of the most complicated because of how useful it is and how diverse its chemistry. I have an acid right there, HCl. Same equation as before. I have a base. You'll need to make decisions fairly soon as to which is the acid, which is the base. And then on the right-hand side, I get the balance. And I'm telling you in this K is greater than 1, that needs to mean something soon. I'm telling you it's exothermic. You probably already know that because you've done this yourselves. Well, down at the bottom, I'm using water again. But I've changed the environment. The material I have added to my reaction flask is now basic. It isn't an acid anymore. It's basic. So it turns out now water has changed its role. Water is now the acid. And you've seen this word before, I hope. It's amphoteric. It can do both, depending upon the environment. That's the key phrase for chapter 3. The chemistry, the outcome, the stability, which side is favored, whether the equilibrium constant is large or small, is all based on the environment. So you very quickly have to be happy with the fact that this is a base. Why is it a base? It's got lone pairs. It's negative. It's basic. Whereas above, in this case, this was an acid. It has a proton. It has an electron poor piece that can be gone after. Everybody okay at the back? I'm shouting because people are falling asleep. And I like shouting. I think we should shout more often. Starting at a very simple, very user-friendly place, let's think about mechanism. This curved arrow notation is key. Get it? You do well in this class. It's the best class you ever take. Don't get it? It's my problem, my fault. Yeah? You take organic chemistry 5 times. You don't do that. And I'm trying to show the interaction between a base. I'm trying to show the interaction between the sticky part on a base, the lone pair. And we'd argue for most bases in our examples here that this is delta negative. It's usually going to be some nitrogen, oxygen, something like that, which already is delta negative, and it has lone pair, which can be basic. And we are trying to show the interaction with an acid. Why go for this end of the acid, not this end of the acid? Because that usually is delta positive, and A is usually some electronegative piece that makes it delta negative. So I have, again, the terminology. Electron poor, electron rich, they go after each other. Now the arrows they have to make sense, okay? They have to go in a set direction. It's like driving. What side of the road do we drive on in this country? Do not get this wrong. The right-hand side, okay? Whereas in Britain, we drive on the correct side. You drive on the right-hand side. It's always interesting going home and I have to wake up after a flight from the States to Britain and I have to drive on the wrong side of the road. That's fun. But we do, when in Rome, drive on the right side or else you get in trouble. The arrows start at the lone pairs. They don't start at the positive things. You're getting them backwards, switch them. You start at the lone pairs, you go for the positive thing, not the other way around. And you obey simple rules. Like driving. What does yield mean? What does Y-I-E-L-D mean in this country? It means stop or give way. It doesn't mean speed up and try and get, as it usually does around here. We have conventions to make things make sense, to keep things safe, to make things explainable. In this case, the electron-rich thing is going after the electron-poor thing every time, not the other way around. So we are starting to draw mechanisms. And we'll extrapolate this in recitation and in class on Wednesday and Friday to more complex systems that you haven't seen before. Very quickly, you have to identify the base. Why is this basic, even though this guy over here has electrons? And the answer is because this has got a negative charge, and therefore it's more reactive, it's less stable. And if I want to attack this molecule, we'll find now that a lot of this is based on the fact that the H is delta plus, the O is delta negative based on electronegativities, and so of course, electrostatics, the negative thing goes after the positive thing. Now that first arrow to me makes lots of sense. This is sticky, it wants to share the electron density, there's something it can share with. Why do I need that second arrow? To show electrons going away, but why is it necessary in the first place? Delocalization will come in a second when we get into that. But why can't I just put one arrow pointing to that H and that's it? It had too many electrons. That's going to be a fundamental issue as you start to practice these things. You'll have too many electrons. So the number of arrows is not random. The number of arrows is set to explain something logically. In this case, to make sure that nothing breaks any octet rules and that we end up with charges in the right places. Now, Sarah, you sort of alluded to it there. I have a conjugate base over here. I have a base over here. Your job now will be to work out which is better, which is weaker, which is stronger. And in this case, give me a word that describes that charge on that oxygen. It can't go anywhere. There are no pi bonds. What's that word? Localized. And what about over here? What can I do with this charge on this oxygen? Delocalize. You see you're applying it now? You can delocalize the charge on the right. Which is more stable, the stuff on the right or the stuff on the left? Stuff on the right because of that delocalization. So which is the stronger acid? This stuff or this stuff? Go on the left. Yeah, the converse relationships between the acid and its conjugate base. A lot of it based on things like stability, based on electronegativity, based on size. Okay, those very fundamental principles now come into practice. So what we'll do on Wednesday is start to think, I've got to get to recitation in 5 minutes. We will do more practice problems. We will build up equilibrium constants. And let me finish. You'll have to learn this. If you are ahead of things and you want something to do, if you're keeping up with stuff, you want something to do, go learn those numbers. You need to know them by Friday. right? Learn that pKa table. It's a condensation of all this stuff from the book. Learn that table, and you'll be doing yourselves a favor.